In this lesson, we are going to learn one special case of gamma distribution, that is exponential distribution. Okay, so the notation is x follows exponential lambda, and exponential lambda is same as gamma 1 comma lambda, where alpha equals to 1, right? So when alpha equals to 1, this is simply exponential distribution. Now the PDF of gamma distribution is lambda to the power alpha, gamma alpha, x to the power alpha minus 1, and e to the power minus lambda x. So when you put alpha equals to 1, you'll get the PDF lambda divided by gamma 1, x to the power 1 minus 1, e to the power minus lambda x. So this is lambda e to the power minus lambda x, and this is the PDF of exponential distribution where x is greater than 0. All right, now if you remember, the mean of gamma distribution is alpha by lambda. So when you put alpha equals to 1, you'll get the mean of exponential distribution, which is 1 over lambda. And similarly, the variance of gamma distribution is alpha by lambda square. So the variance of exponential distribution will be 1 over lambda square. All right, so you can say in exponential distribution, mean is equals to standard deviation, and you can equate this because the unit of mean and standard deviation are basically same. Okay, so mean is equals to standard deviation. Now let's look at the CDF of exponential distribution. So the concept behind the CDF is you basically integrate from the lower limit of x up to some point x, right? So the lower limit of x is 0, so you'll integrate from 0 up to some point x, and the PDF, so the PDF is lambda e to the power minus lambda. Now let's say s, because we already have x on the limit, so we have to assume some dummy variable. So lambda we can take this out from the integration. So this is 0 to x e to the power minus lambda s ds, and the integration is e to the power minus lambda s minus lambda 0 to x. Okay, so if you solve this, you'll get 1 minus e to the power minus lambda x, and x is greater than 0. So this is the CDF. You can also write this as probability x is less than or equal to x. This is same. Now you can also derive the formula for x greater than x, which is simply 1 minus e to the power minus lambda x. So this is e to the power minus lambda x. Okay, so these are two formulas that you can remember. It will help you to calculate the CDF quite easily. Now let me ask you one question. What is the median of exponential distribution? So median of exponential distribution. So let's derive this. So let's say the median is m. So the median is the value of m such that probability x less than or equal to m is 1 over 2, right? So up to the median, the probability or the area is half. Okay, so probability, we can write x less than equal to m. We can also write this as, right, these two are basically the same notations. So we can say 1 minus e to the power minus lambda n. This is the CDF, right? And this is equals to 0.5. So you can find out the value of m. So e to the power minus lambda m is equals to 1 minus 0.5, which is 0.5 minus lambda m. You can take log on both sides. So this is log 0.5. So m is log 0.5 divided by minus lambda, right? And you know log 0.5 is log 1 over 2 divided by minus lambda. So m is log 2 to the power minus 1 minus lambda. You can bring this minus 1 in front. So minus log 2 divided by minus lambda, which is ln 2 divided by lambda. So the median is m equals to log 2 divided by lambda. All right. So this is the median of exponential distribution. Now let's look at the application of exponential distribution. So one example of exponential distribution is it is used to model the waiting time t from one event to the next, in a Poisson process with rate lambda. Okay, so let's do one example so that you can understand better. So in this example, claims to a general insurance company's 24-hour call center occur according to Poisson process with a rate of 3 per hour. Calculate the probability that next call arrives after more than half an hour. So here the number of claims, let's say this is x, in an hour can be modeled as a Poisson distribution, right? If you recall, then Poisson distribution models the arrival pattern. Here the number of claims is the arrival pattern, right? With mean lambda equals to 3. As you can see, average rate or constant rate, this is lambda equals to 3. So in this case, the waiting time, let's say t, between claims can be modeled as an exponential distribution with lambda equals to 3. All right. So now we can calculate probability waiting time is greater than half an hour, that is half, and you know the CDF, which is e to the power minus lambda, which is 3, and x is half. All right. So this is nothing but e to the power minus 1.5, which is 0.2231. So this is how you can use exponential distribution to solve this kind of questions. So this is just one application of exponential. Okay. Also, exponential distribution has the memoryless property. Now recall that geometric distribution had the memoryless property, right? So exponential also has the memoryless property. So this means probability, that is the conditional probability, x greater than x plus n, given x is greater than n. So we can show this as probability x is greater than x. If you want to prove this, then let's do it. So the common between these two, the intersection between these two events is probability x greater than x plus n divided by probability x greater than n. And we know the CDF of greater than, which is a to the power minus lambda x plus n divided by a to the power minus lambda n, and we can write this as probability, sorry, let's do one more step. So this is a to the power minus lambda x, and this is nothing but probability x greater than x. So this proof is very simple. Now there is another special case of gamma distribution, that is chi-square distribution, and we have already talked about this in the previous video. So in short, I can tell you that chi-square distribution is used to calculate the CDF, or the probability for gamma distribution. Okay, for now let's look at beta distribution. Before this, let's recall beta integration, that is from 0 to 1 x to the power alpha minus 1 minus x to the power beta minus 1 dx, and the answer is gamma alpha gamma beta divided by gamma alpha plus beta. So now we can bring these terms to the left side. So this is 0 to 1 x to the power alpha minus 1 minus x to the power beta minus 1 gamma alpha plus beta divided by gamma alpha gamma beta, and this is 1. And we know that alpha and beta are positive. So, and the value of x ranges from 0 to 1, right? So these terms will be basically positive, and the integration is 1. So this whole expression will be the PDF. So the PDF of the beta distribution is x to the power alpha minus 1 minus x to the power beta minus 1 gamma alpha plus beta divided by gamma alpha gamma beta. Okay, where x ranges from 0 to 1. Now let's look at the mean and variance. So mean is alpha by alpha plus beta, and variance is alpha times beta divided by alpha plus beta whole square times alpha plus beta plus 1. We are not going to derive this. You can simply remember this and apply it in questions. Okay, now let's just stop here, and I'll see you in the next video with some other distributions or some other concepts. Okay, so thank you so much for watching this video.